Cool. Well, thanks very much for showing up. Ones of you that have shown up. So, first question: how many of you have had graphics before? I said yesterday, roughly. Good. No one. Okay, that's a safe choice. But even if you have, you can just intervene and bring in your experience to some extent. There is a bit of an overlap with the graphics course, which is running at the same time. So I explicitly mentioned that the ones that actually have graphics background, they may not necessarily take away much from it, but the ones that don't, I think should get a good insight of what's possible and what graphics on Android actually means, right? Or graphics more generally. Yeah, so that's kind of the message here in advance. So today I'm just talking about how can we integrate some graphics programming into mobile devices. In fact, we're not actively doing it, so we know assignment that requires it. If you, of course, want to dig in and do it as part of this project, find a project for this course, you'd be more than welcome to. In fact, it would be quite interesting. But of course, it's kind of a bit of a threshold to actually get going, right? So if any one of you is keen exploring that, feel free to. But today, it's more about principles of graphics. So none of you has heard the graphics course, right? So just so I can pitch it right. Good. Cheers. Okay. So when we use graphics, right? So we usually go beyond text representation, and we use graphics for representing complex object, visualizing stuff, be it graphs, of course using games, but also to advance our UI or UX features to some extent. In fact, you're using graphics for which assignment right now to some extent? No? No graphics? Yeah, please.
Assignment 3.
Yes, right. So you have graphical elements that you use in there, right? So fundamentally, it's about having some sort of, animations, if you like, right? So also those are considered graphics. However, of course, 2D graphics, right, as you may have guessed. But nevertheless, those are graphical elements. But today we kind of want to look into what's possible both in terms of 2D, but more importantly in terms of 3D. That we want to use. And the obvious application case is, of course, games, right? So you guys frequently, I assume, play mobile games to some extent, and then hopefully also have explored some 3D capabilities there of your mobile device. So it's usually about going beyond just menu and text rendering as we're used to, right? So, so if we think about 2D representations, it's usually about flat images and given locations, and you move them around, right? So that's kind of the interaction that you probably showcase on the device, right? 3D. So, what is the fundamental challenge in 3D, you think? Please.
Maybe the graphics processor of the phone itself, like it's more graphically demanding of the machine.
Sure. Yeah. But think about more.
Also, like you have another axis to deal with, so the logic gets more complex.
Aha. Why?
I guess collision and such. You have 3 points to keep track of.
Mm-hmm.
Well, when you do 2D, it's just X, Y, such and so on and so forth. I think it's a bit more simple to do the math.
Yeah, definitely. So the math is more simpler, much more conceptually simple. That's right. But if you think about, that's absolutely right. Right, you're spot on. Right. So what I want to get at is here. But what would you need, what do we actually do when we model 3D on mobile devices? What is the fundamental output that we're producing?
2D image that looks 3D.
That's right. That's the thing, right? So we're taking 3D and making it 2D again because, surprise, surprise, our displays only have 2 dimensions, right? So we don't have a holographic display available in our phones, right? So that's the thing as well. So it's not, of course, it's a high complexity in terms of calculating, thinking about collision, right? Because you need to think about 3 dimensions suddenly, right? It makes it a bit harder than just the conventional 2 dimensions, as you know from Pac-Man or the like, I guess. But they're thinking 3 dimension. But worst of all, after you have created the 3rd dimension and modeled everything correctly, you need to bake it down back into the 2-dimensional display on the phone, right? So there's a lot of challenges involved with this one that some of them we talk about in a bit. But fundamentally, how did people before us do it, right? So, and if you talk graphics, people often think, okay, cool, mobile phones, OpenGL, Vulkan, let's go. But actually, it's sometimes worthwhile just to look back. So I'm digging a bit into history, so it becomes a bit of a history lesson here. Yeah, throw rocks and potatoes if you feel like I should go back into the technology perspective. But I think it's worthwhile looing back because it tells us something about how graphic actually works, right? So we see here on the top right caveman paintings. Where are they from? You guys know that? Ah, it's written there, I know. So I'd hope that the artifacts are so coarse that no one would figure it out. Probably, yeah.
Well, again, right, quite read what's on the page, but are those like those cave paintings in France?
That's right. Those are the fundamental, one of the oldest known cave paintings, right? So especially in Europe, so very, very famous because they represent some animal, I think hunting scene. I think that's the depiction here, right? So you know, and it progressed over time. There are certain meaning associated, of course, with those pictures again. But more interestingly, we also see certain you know, representation of real events that are meaningful in lives of people, hunting, celebrations, ceremonies, and the like, classical ones, and they generally center around depiction of real objects. So they don't have an abstraction level as we do nowadays, right? So if you have abstract representations of something, think Pac-Man again, it's rather abstract if you like. That's not really the case here, but they are, this time they came up with a lot of representational conventions already. Do you see some conventions on those pictures? Do you think patterns of what you, it's probably challenging to see because you're so acquainted with this, but they actually share, some of them share given conventions, some of them depict individual conventions. Any ideas?
Everything is in profile?
Yeah, that's right, yes. So that's something that, yeah. What else?
Don't like paintings to really have this thing called the golden ratio.
All right, you're talking about the golden ratio. Do we have that here?
I'm not sure, but I know it's a thing.
That's right, that's a thing, that's right, it's a thing. I don't think any of this one displays it. That was a bit later, I believe, when you know we came into architectural drawings and things like this. So aesthetics, very good point. Yeah, definitely, +1, yeah. Any other conventions you see there?
Most of the things are facing right.
Exactly, right? Left to right is one convention, so story progresses from left to right, okay. You know, someone came up with this and everyone bought into it, so it seems intuitive that everyone is walking forward when they're pointing to the right and backward when they're walking to the left, right? You know, so anyway, so just to give you some impressions of conventions. So what other conventions do you see that relate a bit more to 3D representation? Yeah. Please.
I guess like foreground, background.
How did they model that?
Like the foreground is bigger, so it's closer to you, whilst the background is smaller.
Correct, right? So we have foreground, background characteristics here. We have this layering here implicitly, right? So different horses riding next to each other actually modeled as very fashion to model foreground, background. It's hard to see. If you want to switch on light, you'll probably see a bit more. There's a lot of pictures today. Cool, yeah, that's right. So basically playing with size, the obvious one, right? But it's not really systematic. It's just, yeah, make it smaller, it's probably in the back, make it bigger. Yeah, I guess in the front, right? It doesn't give you an absolute appreciation of how large the animal actually was, right? So it's really hard to gauge what's the relative size between the animals. You just know the one, you know, was further away than the other one, right? Another interesting representational convention on the right picture. Do you see anything there? That's something you can take away if you go to next time to your art gallery and then you also related to 3D representation, which is problematic for a particular artifact on those pictures. Since you're not doing it, I'm doing it. Right. Beautiful. Appreciate art. Wonderful. Anyone? No, I don't see you anymore. Oh, that was clever. Yeah, please.
Well, guess lighting. Like, you can see the right at the bottom left corner, it's a bit more brighter. But like the deeper in you go, it gets a bit more shaded underneath the trees.
Ah, interesting. I didn't see that. Yeah. Representing a light and it's a dark forest, the hunting scene, right? That's for sure, yeah. Look at the weapons. I wonder how ages on it, but what weapons do you use?
Crossbows.
Sorry?
What are crossbows?
Rifles?
Crossbows.
Crossbows, right, that's the one, right. And what is particular about the crossbows? Is that how you shoot crossbows? No, right? How do you shoot crossbows?
Horizontally.
Horizontally, right? So what happens if you have 3D representation of a crossbow from the side? Exactly, it looks like a straight line. You wouldn't be able to recognize the weapon, right? So that was one of the ways of accommodating 3D representations in paintings as well by convention. So if you have weapons, for example, that would otherwise be obscured, they are drawn sideways, actually, right? So it's physically inaccurate, but it's from a conceptual insight, it's quite important to actually see that, right? So 3D was an important problem, right? That people dealt with in different ways, right? So sizes, foreground, background, layering, and representational conventions, which are actually at odds with the physical reality. Yeah? So it's not a new problem in principle. So all right, a lot of ad hoc solutions and conventions, but they are not really, they're sacrificing reality to some extent. When finally in around the 1420s, now it comes Brunelleschi, there you go, kind of figured out, okay, there's a thing called linear perspective, right? And you probably have seen that before somewhere, perhaps perhaps even in Wiedergående school, I don't know, in the arts class or something like this. So how do you do systematic drawing, right? That's like drawing for the less creative ones, if you want, because there's some, you can grasp it mathematically to some extent, if you like, right? So if you don't want to just go for it. So the idea of linear perspective is that you identify a horizon, right? So and a vanishing point, and basically draw lines from the viewer's perspective towards the vanishing point. So you have this perception of views, and then you use those orientation lines to actually, position your artifacts or people, figures, and the like, right? You can see this kind of ad hoc use of a linear perspective here already, right? So it's quite obvious that we have a vanishing point, which is, I don't know, somewhere there, I guess, right, to some extent. Anyway, so it's quite clear. So you find this often in medieval paintings, that you have this conception of vanishing point, sometimes less accurate, sometimes more accurate, but fundamentally that's the insight. Well, how there's a famous experiment associated with this, and I'll just briefly highlight the experiment. Brunelleschi, that's, I always get the name wrong. Anyway, was the architecture of the largest brick dome up to today. Anyone of the arts inspired know where it's located? Largest brick dome, the dome only mostly. It's in Florence, right? It's in Italy. So if you get there, have a look. It's probably worthwhile seeing. I haven't been there yet, so I'm of course, walking on thin ice here, as you can imagine. Being an arts teacher by trade, yes, you see that. So the Brunelleschi experiment was as following. So in front of the actual dome, there is a baptistry, this thing, right? And his idea was, okay, how can we systematically grasp drawings? Because it was particularly important. He was an architect, he was not an artist. I mean, he was also, I think, an artist, but particularly interesting for him was the architectural perspective. How can we actually produce or start to produce accurate architectural drawing that we can use for construction, right? A serious problem, right? You can't just paint randomly and say, yeah, cool, that's in front, that's it back, good luck. It kind of needs to fit somehow and work out, right? Conceptually. So he conceived that experiment here. And the idea was relatively straightforward. So it was basically about identifying the horizontal line, okay, that's something he came up with. Then the having vanishing point, we see in this example here, if you see the drawing, there are two major vanishing points. Following this idea, he basically drew the building then on a canvas, right? So following its representation, and then he basically punched a hole at the center of the representation, the door of the very dome, and then held it in front of his face, facing towards the dome itself, and using a mirror, and lifting the mirror and lowering the mirror to validate how accurate his painting was. And it turned out that this allowed a validation of an accurate depiction of the actual baptistry, right? So that's the idea. So this was the first major experiment to ensure that you have an kind of geometrically accurate perspective representation of an architectural building, right? So, and this was then basically considered, because it was so successful, it was considered groundbreaking in terms of particular architectural drawing, right? So suddenly there were a set of mathematical rules, basically the proof of the vanishing point and horizon line used to draw linear perspective for futures of architects or I guess impressionist painters as well. So that's quite important. So if you come across that thing, and of course it follows us up to today. Same concept. If we do a 3D representation, you know, it's a similar thing. Very straightforward. We have a horizon vanishing line, and if we orient those objects there, we see that very effect, right? So quite straightforward concept that we still borrow and follow when we do some development. So Da Vinci turned it around. Fundamentally, okay. So how do we do this a bit more ad hoc? Can we make it even easier for the less acquainted to actually draw a architectural, you know, an object with certain accuracy? He came up with the Perspectograph. Think about a frame, glass in between, or glass canvas in between. You draw on this glass canvas basically, and afterwards you transfer to you know, your actual canvas, and then fill it up with color and stuff. So the color thing wasn't solved, but it was only about the geometry and the perspective representation here, right? So, and if you think about this, it's all about, the whole exercise is always about how to bring 3D onto 2D. Yeah, that was the fundamental problem they solved. Brunelleschi, I need to stop saying that name, and Da Vinci as well, right? So they're all looking at the same kind of problem, slightly different approaches here. And one thing you of course know, another perspective that I expect you're kind of fairly acquainted with, is the camera obscura. Who did this in high school? Physics, optics, probably? No? Who built it at home somewhere? No? Who knows what it is? Floor is yours. No one? So, following idea. So you basically have a closed room. So that was the original conception. You have a closed room, darkened room, and you have one pinhole in that particular room, right? So, and the idea is there, if you have a light source coming from the outside, this room needs to be dark, very dark, and you have a canvas, or you know, a wall, white wall, whatever really, some sort of projection plane on the opposite side of this hole, then it will provide a, and if the focal length is correct, that is a given in a way, then it would provide an inverted depiction or projection of the outside image onto that particular wall. So you can build this thing yourself. You basically have, you know, use cardboard, black cardboard, close it up on one side, the other side make it somewhat semi-transparent, put semi-transparent paper on there, and then on the opposing side punch a hole into it and just positioning it towards some object. For example, a candle is a good one because it's emits light, right? So, and then you should see an inverted picture, so upside down representation of that candle in that camera. It's nice, you know, yeah. Basically to show optical principles of how they work and how projection works. So that's a practical use basically, and fundamentally the motivation for you know, first cameras, of how we actually can produce and record pictures. The thing is, of course, how do you keep or make those pictures persistent? Well, the exercise was basically you need to draw from that wall onto the canvas, you know, or find some way of transferring it so as to keep the picture permanent. But it basically allows you to create a primitive photograph. And this idea, this knowledge was actually very old. It was actually before 500 before Christ already that they come up with this idea for mostly ceremonial purposes. And but only in the second half of the 16th century, that's why I'm putting it at this stage, it was systematically used for actually providing accurate depictions of some objects or the like. So that's why we sometimes have really accurate representations of architecture at that time. So yeah, so while the key difference here is though, while the Perspectograph, meaning the Da Vinci thing, did something similar, it was they have slightly different objectives. Here it's really about just getting an image of reality. In the other case, it was constructing reality from mathematical principles. Yeah? Here's just, ah, cool, I have a picture done, right? So in the other case was, how can I systematically analyze a drawing or analyze architecture? So a slightly different objective, not for everyday use, I guess, but this one was closer to what we would think about as a camera nowadays, I guess. Okay. So how does that in principle work? Here's another depiction, same principle. Well, pinhole cameras, that's the modern term for the camera obscura. So basically you have a very straightforward, simple geometry. It needs to be dark inside, that's the main thing. And the idea is then that you have an example of a perspective projection, because it basically depends on the depth of that perspective camera to translate the dimensions of that tree, right? So the screen representation is a factor of the focal length that actually your pinhole camera provides. So basically, the longer it gets, the bigger a picture gets, right? So quite straightforward, no magic there. But anyway, it's just a symmetric perspective representation, and this would be the systematic approach of addressing it. So you have some sort of projection plane. You have a center of perspective, right? So from which you're basically viewing the scenery, if you like. And the idea is that if you're depicting reality, so in the far end, basically there, the size of what you're representing is a fraction of the distance between the camera and the projection plane relative to the distance from original point to the object of interest, right? So that's the idea, and that would basically depict the size. So if you need to calculate x, the x value, you do that basically by multiplying it by the distance between center of perspective and the x-axis, so the actual distance to the object. So that would give the reduced size of the image. That's called perspective projection, that's right. Okay, so this is fundamentally, hang on, kind of nearly everything we need to do in order to represent realistic pictures in some sort of computational screen accurately. We just need to reduce the perspective of the object that we want to deal with, right? So, but more interestingly now, so that was kind of the graphics background, or the principles rather underlying it. But what does the computer actually see? How are images, for example, actually represented in a computer? Please.
Does binary code?
Yeah. So example. Yeah. Okay. Cool. Binary. Yeah.
Yes,
you get away with this, right?
Is it like it says that this pixel is this color, this pixel is that color?
Correct.
And then like each position of each pixel?
Yeah, that's right. So so there's two components in there, right? So one of them is positioning, right? You send so each pixel. That is basically an intersection of x and y, right? So axis in the 2D image has a particular position in the image, and then you said something about what? There was something else.
Color.
Color, right? So how is color represented?
Depends on the type of screen.
Yeah.
It's usually, I don't know, 1 of 4 types, like red, green, blue, whatever.
Yeah.
Then it is like you're connecting like batches of 4 and 4 or something.
Uh-huh.
They like combine the colors to get different colors.
Right. Yeah.
Each color is represented by some bit, I suppose.
Right. Yeah. So yeah. So you're fundamentally right. It's about breaking down to the basic colors that we humans perceive. So and otherwise, computer vision would be pretty useless for humans. And that's indeed RGB, red, green, blue, right? So, and then they're combined and associated with a particular position, right? So abstractly speaking, if we think about an image, right, so on the left side, that would be what we kind of see. On the right side would be what the computer kind of sees. And the essence here is to get around, of course, that's a very abstract representation here. But if you, the essence is about it, unlike us who actually think in terms of objects, right? So in the context of perspective projection, it was always about scaling objects, drawing objects, systematically reconstructing objects. The computer doesn't have any of that semantic information, right? So it's merely color information and brightness information generally, right? So that's encoded at particular given pixel positions, right? So the fact that there's a locomotive depicted there is utterly irrelevant from a computer point of view. It's just a set of values that is set. So yeah. Okay, so if you think about pixels, yeah, it's basically intersection of x and y depending on the resolution of the picture. This kind of pixel, the square is smaller or larger, of course, right? So, but this needs to be somehow colored, right? So, and the motivation there, surprise, surprise, comes a bit from human vision, of course, because what we see is across different a range of wavelengths, right? So we have we have a set of cones and rods in our eyes, right? So they have different purposes. Rods are used to actually see ambient light, so we can differentiate brightness, brighter with darker situations. So it's primarily relevant when we are outside at night. We're actually not good at seeing colors at that stage, but we're good at recognizing, well, reasonably good at recognizing shapes still, right? but differentiating is a nightmare, so it becomes a bit of a tricky one. But as soon as you have enough light information, actually cones come in, and they actually combine the individual color information across different wavelengths. For example, blue cones are more sensitive to lower wavelengths, around 420 nanometer, whereas the higher, what is it? Yeah, the green cones and red cones are closer together. So the conflation between those two ones is the human eye is more sensitive to those images. To the conflation of those different colors. So it's much easier to confuse red and green for us than it would be, for example, to confuse red and blue for us, because the wavelengths are so far apart. But fundamentally, those are the three wavelengths that we actually actively perceive with our eyes, because we have the corresponding receptors for those ones. So the cones, and then they are combined internally using this additive approach. So basically we have the individual colors, and by overlaying them respectively, meaning by having overlaying information, they are additively combined up to an extreme value of white, right? So if all rods are activated, basically across all colors, we see white. If nothing is activated, we see black. Well, mediated by the rods that probably perceive some sort of brightness independent of color. Right? So that's the rough idea here. How we see things, and that's why computational computer vision is kind of modeled around this principle. Right? So it actually also uses the RGB scheme to represent individual pixels. Right? So if we see that here, for example, if we break it down, then suddenly an individual pixel along this DS ear here is represented in a corresponding color combination. So we have green surrounded by then an overlay of what that possibly would be, I guess a bit of blue in there here and so on. Anyway, you get this color overlay to get a differentiated perspective. And in order to describe the quality with which we can represent images, what are the two metrics that are important? For example, if you have a picture format and want to say, hey, we want to perceive highest possible or have highest possible quality in representation, what are the two metrics that we usually would think about? Please?
Height and width.
Pardon, sorry?
Height and width.
I simply didn't get it.
Height and width.
Height and width, yeah. So what boils that down? What's the term that we resolution, right? So resolution. So what's the resolution of the image? You know, can I scale it up? Look at this, right? So yeah, no, probably not, right? So if you expand this D onto the whole screen, it probably looks closer to this artifacted representation. So resolution is important. How small are the pixels? That's number one. What's the other parameter that's important for an accurate representation of reality?
Perhaps the screen size itself.
That is relative to the resolution, right? So if you have a smaller screen, you get away with smaller resolution, right? So yeah, so it's kind of it's an interplay with the resolution of the actual image, right? But less device dependent. What's another important information in order to have an accurate representation? What fundamentally happens if we break down, right? So the color information that we have, we need to break it down in some sort of value. Right? So we combine red, green, blue, and so on, and represent this as some sort of value. In the extremal case, if you put it this way, what would decide how nuanced the color representation would be? What would be decisive to do? There would be a way of doing this. We think about color as something continuous, right? So you have a green that becomes increasingly greener. I think about a slider, right? So like this. But a computer at some stage actually needs to discretize it, right? It's not a continuous value in the widest sense, or it's not. But it needs to actually be discretized, right? So we need to have concrete values to represent the extent of green, the extent of red, and the extent of blue, right? So what could be another aspect that's important in picture formats? If you had lived in the 1990s actively, you probably would remember that. basically color depth, right? So the idea, how nuanced can I represent different, how nuanced can I represent different shades of green, if you like, right? So, and usually color formats have something like, okay, you can represent 8-bit colors, 16-bit of colors, or 32-bit of colors. What is 8-bit 8-bit representation? How many colors can you represent with 8-bit? Convert to decimal, 8-bit decimal.
50, 60.
Okay, coming back to first year. So what's the decimal value of 8-bit? That's right, right? So the idea is there, if you had a 8-bit depth representation, you would only be able to represent per pixel 256 colors, and then you get those really obvious changes in color. You have very limited color. Think about, you have 16 colors to represent in worst case, right? You can probably imagine how an image looks like with this, right? It's probably not even close to what the human eye probably would see, right? So the depth is decisive in terms of allowing you a nuanced representation. So if you have 8-bit, you're certainly not getting far with 256 colors. That's very coarse-grained for photos. So that's okay for schemas and like Visio style visualizations or UML diagram. Doesn't matter for too much there. I mean, it's better than having 1-bit, which would be black and white. So it gives you some nuance in terms of color schemes. But for pictures, you actually want richer ones, right? So 256 is borderline, and then we have 16-bit, which would be 65K. So 65,000 different possible colors per pixel, right? And then going on from there, 32-bit. So you get the gist that you have a much more accurate representation of reality if you allow a different bit range in the representation. So different image formats support, well, not so much resolutions. Resolutions are fairly independent of that one. Nowadays, I think anyway, I don't think there's any image format that really delimits you specifically with respect to the resolution. But more importantly is the depth, the color depth that you can actually capture with your image file, right? So if you look at BMP, a classical Windows bitmap thing, it's quite relatively straightforward in representation. I found this because it's kind of a neat, representation by analogy to some extent. Of course, you have a header. It's a hex editor representing a subset of an image here. So we have a header that basically identifies it as a BMP file, some sort of offset in the beginning and meta information. Let's not worry about this. But more interesting is that how the image is actually represented, right? Because we have, where are we? Ah, there you go. We have the RGB value representation. So red, green, blue, right? Representation in hexadecimal form. For the first pixel down here, then for the next pixel, for the third pixel, and so on, right? So you can modify and manipulate the picture by playing around, of course, with this representation. So that would be an example of a simple internal representation. There are more advanced ones, especially when it comes to compression, because as you can imagine, it's quite expensive in terms of size. I mean, the image would be rather big if you don't compress it, because fundamentally it's text information. So the advanced formats such as JPEG and so on do that actually, right? That they compress, identify areas of images that have the same color and simply reduce it to one value, right? So that's why it's so-called lossy, that you actually lose nuanced information, right? If, for example, here, if you can reduce this entire area, say, come on, there's roughly the same color, let's make that brown, done, right? So then you would have one representation for this entire area. You just say, those and those pixels all have that color information, right? So of course it implies you lose detail, right? So that's one of the idea of having lossy compression. But in lossless cases such as BMP, you would really represent each individual pixel, even though the adjacent pixel may actually have the same color. Does that make sense? Simple form of compression in images. So it's super efficient on larger images, especially if you have large areas of homogeneous color. Anywho, so I don't want to go too deep in this, just the principles, right? How a computer represents. Is it somewhat clear, intuitively at least, right? So you kind of break it down into RGB values. You have different color depths representations, different range of values, which of course explodes, complexity or size of your picture. But fundamentally, you have formats that support it, and there's various ones: BMP, PNG, TIFF, and so on. All for the GIFs, for example, for different purposes, also including some of them animation, meaning they include multiple pictures that are played in sequence. We get to that in a second. So we'll come back to games to some extent. So if you think about traditional 8-bit games, the idea was usually taking those little images, right, overlaying them systematically, and just having them react to user input. So fundamentally, it's basically just the sprite is a small image that kind of moves independently of the background or relative to other objects. I think a classic one is Time Pilot. I'll just bring up the video to give you an appreciation because it's quite visible there, I believe. I'll spare you the advertising. Xevious is the game. That's a long advertising. Anyway, so yeah. So this is like hang on. All right, it's only 31 minutes, so bear with me. So, but now fundamentally the idea is Xevious, very old game from 1982, if I got it 83, sorry if I got it right. But fundamentally straightforward. You have a background, right? You have a fixed background. That's the image that you actually move, right? And then you have a set of smaller sprites, like this guy here, for example, right? That just moves around. And all the individual bullets and so on are all individual objects. You see those ones turning, for example. That's quite relevant. So there's an animation component. We look at this in a second. But fundamentally, that's all that's happening there. It's a combination of individual sprites or images that are just put into meaning by combining them. And basically, it's mediated by interaction, really. But fundamentally, it's just an overlay of different images. As long as you get the order right, you have the perception of 3D, right? So a bit like, it's not a 3D game, of course, but you have a perception of 3D movement to some extent. See if we see. I'll briefly bring this up because I want to show you some other feature that is quite interesting. Let's see if we get right. So, sorry for the advertising. This one is called Time Pilot, also quite old game. Oh, yeah, okay, old game. And here you have the same kind of principle. So you basically have images in the background, right? But here you actually see very explicitly. So it was kind of an advanced approach where we basically used the parallax approach. That was, we have now multiple layers. We're not only having the blue background here, but there's also a layer in between. You see how the clouds actually move across each other, right? They're not sitting at the same plane and moving alongside each other, but actually there's a kind of perception of third dimension. Do you guys see that? I don't see you right now. So so here, for example, is a good example that you see there's another layer that's moving across the different layers. So it was giving an even richer perspective of pseudo 3D in a 2D environment, right? So so you actually have the perception as if you can fly along the z-axis, means it's into the picture in principle, even though that's of course not happening. But fundamentally, it's just shifting around pictures. So while it was considered challenging at that time, nowadays, of course, it's kind of a very cheap approach, right? You just get the positioning of 2D sprites, 2D images right, and as long as you do that, you get this effect here that we see. Let's get rid of this. So just to give you a feel. So that was basically the first generation games that were those ones, right? The first one you saw was this Xevious game. The second one, Time Pilot, was a bit more advanced. You guys, do you know Pac-Man? Sorry, GTA. Sorry, the first one. And 90s, basically similar, right? You probably know the modern GTA, which is of course 3D and so on. That's not what I mean. The first one you actually see from top down. Similar, they had also had parallax effects to some extent. But that's the fundamental idea, right? So, and then if you want to do animation, we saw, for example, that in I think, yeah, we saw here some animation before that actually those coins or those satellites or whatever it is really, they turn over time. And this is modeled using sprite sheets. So you actually have a series of pictures of the same objects at different animation stages, right? And if you run through those ones systematically, you will see that suddenly you emulating a turn of that plane, for example, right? So, but what fundamentally happens is just you're systematically consuming this sprite sheet and actually displaying this animation while you're actually moving the plane, right? Corresponding to user input, of course, but that's basically it. So you get the illusion of an animation there by just having a series of pictures of the same object. Yeah, sprite sheets, in case you come across it. So this kind of is the kind of a baseline of how to do, you know, retro gaming. If you want to re-implement it on at your own pace or make it a project, that's basically all the principles you kind of need to combine and play with them, right? So there's a lot of magic that happened over time to actually make it, you know, more challenging. But there was always this demand of how do we do 3D to some extent, but still leave it at 2D because the tech was simply there. So now getting closer to actual 3D, so actual 3D, not just fake 3D. The idea is there with modern technology, especially smartphones in particular, specifically advent, you know, iPhones and Android, of course, but there were earlier versions as well, even by Microsoft already. So there are suddenly richer facilities that go beyond the explicit 2D representations and use of images and overlays, but actually allow you to, you know, model in 3D. Model meaning actually have models that are reflect in the third dimension, right? So if we model an object in 3 dimensions, how do we do that? What's the fundamental elements that we need? Yeah, please.
A graphics renderer or something?
Yeah, eventually, yes. But before that, right? We need the graphics renderer. You are spot on. But if you think about the 3D representation, what's the you mentioned that before actually, what's the important ingredient that we now need instead of just what we needed for exactly, right? So we suddenly have a third dimension we need to play with, right? So you need to no longer only think about pixels, but actually having a 3-dimensional representation, if not voxels, meaning they have volumetric pixels in a wider sense. But fundamentally we need to have a point that is defined by 3 axes, right? X, Y, Z. That's one of the principles. Okay, and along with this, what else? Three 3D points. What else? If we're going to get 3D perception. Well, we need different mechanisms to combine those, right? So to actually create shapes, for example, right? So faces, that's generally the idea there. So fundamentally we have points. X, Y, Z, for example, right? So, and the idea is then by combining multiple of those, so X, Y, X2, Y and Z2 basically, and 3 and so on, we can suddenly represent triangles, for example, right? So suddenly we have a basis of creating faces. Most of you probably know that triangles are the basic shapes in graphics modeling, right? Usually used. Then you know why that's the case? Why are triangles so fundamental? I mean, if you have 2 points, right, we get a line. Yeah, not much of a face there, right? So it's just a line, quite straightforward, quite simplistic. But if we have a 3rd point, we can get faces to some extent. So why triangles?
I mean, you can use triangles to build other shapes.
Exactly.
Two triangles makes a square.
Yeah, exactly.
You get also corners, you know.
Yeah. You're absolutely spot on, right? So having triangles, you can pretty much model, at least with a level of abstraction, pretty much accommodate any other geometric form that you want to represent, right? So that's the fundamental idea there. Always exceptions on, but that's why the triangle is so very fundamental from a graphics point of view, right? So you have 3 points, and if you combine those, you suddenly have some sort of plane that you can represent in 3-dimensional space. If you attach the next plane to that, well, you can actually represent a square or a contour already, right? So by angling, for example, the position 4, right? So if you like that. And this is where the whole geometric modeling support comes in, especially in things like OpenGL. So the idea is there that you take individual points in a 3-dimensional space, or you give the system basically all the points you want to render, or not points, vertices. Sorry, that's the right term. No longer points, because 3rd dimension we talk about vertices. And tell the system, well, how do you render those things, right? So here I have 6 points, right? Either you say, well, you know, you don't combine them at all, leave them as are, Or if you say, tell the system, well, you have the 6 points here, please render them using the primitive GL lines. So that's an OpenGL example, but it would roughly be equivalent to other approaches in DirectX or the like. But basically you'd say, cool, I'm modeling lines. So since I'm modeling lines, I can only combine the first and second vertex, the third and fourth, and the fifth and sixth. Because if I were to combine them all, I get a face, right? A surface, right? So if you say, well, a line strip, well, you don't close the thing entirely. It should still be a line, but a line strip. Should it be a line loop? It can be a closed loop, and so on. So you can model a lot of different shapes. If you say, here, take those same vertices, but form triangles, it will pair those respectively and make create triangles out of this. But you probably the thing here that I want you to appreciate is that it's actually rendering is done for you, right? So in modern graphics engine, you provide the vertices, you say how to combine them, but the actual drawing the shapes and so on, it's nothing you need to technically worry about because it's done for you, right? So you just say, as long as you have coherent, organization of vertices in your model, and you say how they are to be combined, then you get the surface of your of choice, right? It's just a matter of getting the model to position correctly in three-dimensional space. So you have those prototypical primitives in OpenGL. They can vary in different languages there, but fundamentally that's the idea. So it goes beyond triangles. So here, for example, you can also represent quads, but fundamentally over time, the library of possible shapes has been, the range of possible shapes can be extended, also by you as a developer. So you can inject new algorithms as to how to combine different vertices into more advanced shapes. I get into that in a bit more. So. But of course, well, some of the fundamental 3D geometric primitives, so we previously talked about planes and triangles as a basis of shaping those, are also available. It would be like classically cylinder, cones, hemispheres, and spheres, right? So that you can combine to create more complex figures, right? So they're considered some of the base shapes that that are also readily provided in many environments. And as you mentioned before, well, triangles are really good because you can combine them to nearly anything. So that would be an example of how we actually develop a concrete model by simply combining a set of vertices and just say, well, here are all the individual triangles, combine them into a coherent mesh, and suddenly you have the 3D perception of, let's say, a face or something like this, right? So facial representation. And you get the point already. How would you induce the quality of your graphics? Exactly, right? So generally you would subdivide and have even more refined vertices here, smaller triangles, right? So smaller triangles and so on, of course. This will explode, of course, your model complexity, but suddenly you get much higher quality graphics. Yeah? So that's the thing about it as well. So you can actually make your model higher quality or lower quality, and that's usually moderated by the number of vertices, the number of three-dimensional points that you inject into the model. But the more you have, of course, the more processing, meaning the more your frame rate suffers in the principle. So there's a bit of a trade-off there that you want. But fundamentally, this captures all the principles that we would think about. And when you combine this quite richly, you get, with other effects, of course, you can do things like this. For example, this is the kind of well-known map. It's called the Rungholt map. It kind of represents a medieval city and so on, but it's kind of in graphics, in order to measure performance to do benchmarking, talked about benchmarking before, especially in the demo circles, they use standardized models. So basically, here's your model. That's the Cornell box. We get to that in a second. This is the Stanford bunny, and this is the Rungholt map. Basically, they say, well, if you have a rendering engine, load this thing and tell me how much memory you consume, secondly, how fast you go. So basically, it's a good way of comparing performance of model loaders or rendering engines or whatever else, right? So and how good it looks. But this, I think, has 6 million vertices, and this bunny is not far from it, even though it doesn't look like it. But since it has a reasonably realistic fur representation, you can imagine that it consumes a lot of additional vertices, right? So it's really refined in its structure. So they are intentionally made, those models are intentionally made to be really complex and challenging to load. If you build a model loader, that's usually good threshold to get to, loading one of those things without using up your RAM. So so the one on the left is actually showing different things. It's actually more showing, we will not talk about this, but things like lighting, for example, that you have lighting, you have reflection. You notice here that there's an element of color bleeding, right? So there's light coming against the wall, and this color bleeds into the object, for example. You have reflection of the background, and so on, right? So there's a lot of additional, of course, challenges that some of them are done for you by rendering engines. Some of them you need to model explicitly as well, right? So, but that goes slightly beyond pure model loading, just to appreciate the complexity. But fundamentally, model loading is the stuff on the right side that we see here. Okay, so those are kind of, well, I guess, theoretical principles of 3D representation, I guess. And with this, I'll probably give you a break of 10 minutes, quarter past, and then I'll talk about coming back a bit to mobile devices and how we could use it there, or how it's used on mobile devices in principle.